Today, let us discuss S and D block elements. You will be surprised at the heading. Why it is S and D together? You will come to know in a few minutes from now. Look here first. First statement, all S, D and F block elements, three blocks of elements S, D and F, all S, D and F block elements are metals. Elements are metals. Of course, I am not referring to hydrogen because hydrogen belongs to its own block. You can't say hydrogen strictly belonging to S block. Hydrogen belongs to its own block. Right. Why? Why it is like that? All of them have one or two electrons only in their outermost shell. If you look at S block elements, their electronic configuration is ns122, and D block elements it is n-1d 1 to 10 and ns sometimes 0 to 2. There are one or two elements with ns 0 also. Palladium for that matter is 4d10 5s0. So, and F block elements it is n-2 f 1 to 14 and n-1 d sometimes 0 or sometimes 1 but ns2. What is that you should observe? All of them have one or two electrons in their outermost shell. One or two. Here you have one or two, here you have one or two, two. So, what if they have just one or two electrons in their outermost shell? They have a tendency to lose the electrons, and an element which has a tendency to lose electrons is said to be electropositive and it is said to be a metal. So, you should not just study about S block. It is S, D, F, all blocks, they are all metals because they have one or two electrons only in their valence shell. Valence shell. So, what if they have one or two electrons? They will have a tendency to lose. They are ready to lose, and the readiness to lose electrons is mainly electropositivity and metallic character. Now, second point, S block elements are soft and they can be cut with a knife. S block elements are soft and they can be cut with a knife. Look at that statement. They are soft, no doubt. Are they softer than butter and cheese? Nay. They are softer when compared to D block elements. They are softer only when compared to D block elements. Therefore, whatever statement we speak in S block, we keep in mind D block only. When I say S block elements are soft, they are softer than D block. When I say S block elements exhibit fixed oxidation states, I indirectly mean that D block elements exhibit variable oxidation states. Okay? Why it is like that? So, the answer to all these questions lies in here. Any question on D block, where exactly minus 2b, I am not referring to 2b, zinc, cadmium, mercury. D block minus 2b, they are called transition metals. They are called transition metals. So, I am referring to these transition metals. Any question on transition metals. What are transition metals? D minus 2b. 2b, what are the elements? Zinc, cadmium, mercury. So, any question, this is most of the time the answer. Not only ns electrons, but n-1d electrons also participate. They also participate. Participate where? Participate in whatever area you are talking about. For example, the metallic bond in S block is very, very less. metallic bond strength is less, whereas in D block the metallic bond strength is very high. Why? Not only Ns, but N minus 1d electrons also participate in transition metals. Okay, let us take an example. So, what is the statement? Any question, any means most of the questions you can answer using that. Most of the questions you should think in terms of, look at sodium 1s2, 2s2, 2p6, 3s1 is its electronic configuration. So, sodium has just one electron in its valence shell. So, in a metallic bond, sodium contributes one electron. Sodium contributes one electron. So, because the electrostatic attraction between Na plus and one electron is less, when compared to an element like vanadium 3d3,4s2, it is a transition element. Here, not only the Ns electrons, but N minus 1d also participate, 2 plus 3, 5. So, between two vanadium atoms, it is likely that 5 electrons are participating in metallic bond. Therefore, the metallic bond is very strong. Therefore, the transition metals, they are very, very hard. They have high melting and boiling points. So, melting and boiling points depend on strength of the metallic bond, which increases with the number of valence electrons. The electrostatic attraction is more, and it of course decreases with size. So, in a given period, where do you encounter D block elements? Say in the fourth period, potassium, calcium, scandium, titanium, vanadium, etc. From left to right, the sizes decrease. Potassium is bigger, calcium is smaller, scandium is still smaller, titanium is still more, like this. So, between two atoms of calcium, only 2 electrons participate in metallic bond. Calcium is bigger, so the electrostatic force depends on internuclear distance also. Internuclear distance is more, and electrostatic attraction is high, charge is high. But look at vanadium, up to 5 electrons may participate. I don't guarantee you 5 electrons are participating. Of course, because of too many electrons, the repulsive forces are also there, but the melting point of calcium is less and the melting point of vanadium is more. So, in a particular period, S block elements are bigger in size, D block elements are smaller in size, and more electrons participate in metallic bond. So, what happens that way? Metallic bond strength increases, therefore, they are hard. So, if I simply say S block elements are soft, you don't understand what I mean. Yeah, S block elements are soft. What does it mean? Softer when compared to D block. They are softer when compared only to D block. Okay. So, second point, soft and they have low melting and boiling points. Low melting points and boiling points. S block elements. S block elements are soft. And what is the opposite? D block elements are hard and they have high melting and boiling points. The reason? Here only S electrons participate, there S and D electrons also participate. You may get a doubt as to why D electrons are participating. Say for example, 3d3,4s2, the energy of Ns is almost equal to the energy of N minus 1d. The energy differences are not very high. Yes, of course, there are some differences, but the energy of Ns electrons and N minus 1d electrons almost being the same, their behavior will be the same. They participate in metallic bond. So, first point, all S, D and F block elements are metals except hydrogen. All S, D and F block elements are metals. You hear the sounds: lithium, sodium, potassium, magnesium, calcium, scandium, titanium, vanadium. So, most of them have UM stands for a metal, I repeatedly tell you. They are all metals. Second point, S block elements are soft. They have low melting and boiling points. They can be cut with a knife. Can you ever imagine iron being cut with a knife? No chance. Can you cut iron with a knife? Joking. What is the melting point of iron? Very high. Tungsten, it is more than 3000 degrees centigrade. So, why are the melting points very high? Point number 1, they are smaller than S block elements. They are smaller than S block elements, and in S block elements only 1 or 2 electrons participate in metallic bond. In D block elements up to 5 electrons may participate in the case of vanadium. I repeat, may. There is no guarantee that all of them contribute. Metallic bond is contributory in nature. Them are asked to contribute 5 electrons, but some of them may contribute 4, 3, 2. It is only contributory in nature. So, you can't insist on contribution. You can't ask somebody to contribute this particular number only, right. S block elements have fixed oxidation states. We discussed this many a time. S block elements have fixed oxidation states. 1A elements always plus 1, 2A elements always plus 2, fixed always. What about D block? They have a host of oxidation states. Manganese, for example, anything between 0 to plus 7, 0, plus 2, plus 3, plus 4, plus 5, plus 6, plus 7. So, there are so many oxidation states. Why? Same reason, not only NS, but N minus 1D also participate. Look at manganese, 3D5, 4S2. Manganese, how many electrons you can give? Manganese will not answer that question. Mr. Manganese, how many electrons you give? Manganese does not answer that question, and moreover it asks, how many you want, tell me. Want 2 electrons? Take 3, 2, 3, 4, 5, 6, 7. Manganese can give up to 7 electrons. You have seen many compounds with varying oxidation states for manganese. Why? Not only NS but N minus 1D also participate. So, you might as well get a doubt. Why are these zinc, cadmium, mercury? What are they? 2B. 2B. D block starts with 3B, 4B, 5B, 6B, 7B. I always use the Roman numbering only. The IUPAC numbering doesn't do us any good. The IUPAC number 3, 4, 5, 6, 7, 8, 9, 10. I am not very much interested in that. 3, 8 groups. 3, 8 groups. 1B, 2B. So, 3B, 4B, 5B, 6B, 7B, 8, 8, 8, 1B, 2B. The elements of 2B, zinc, cadmium, mercury, they belong to D block, no doubt. They belong to D block, but they, in them, if you look at the electronic configuration of this particular group, it is D10S2. 3D10, 4S2, 4D10, 5S2, 5D10, 6S2. D10S2, 2B, total 12 electrons, 10 plus 2. 3B, this is S2D1, S2D5, S2D10, S1D10, you know, this is copper group, copper, silver, gold come here, copper, silver, gold. So, that being the case, 2B. So, here only S electrons participate, D electrons do not participate in bond. Why? Very simple to understand. They are a complete set of electrons. They remain as a separate group and S2. So, here only valence electrons participate. That is why the metallic bond in this group is weak. That is why mercury is a liquid at room temperature. Mercury is a liquid. They are not hard. So, I repeatedly told you, when I say D block, I am not talking about 2B, and from 3B to 1B, they are called transition metals. Only these are called transition. Transition. These 2B elements, they belong to D block. So, from here to here, it is D block. From here to here, it is transition. 3B to 1B. So, why are 2B elements not transition elements in their strictest sense? Strict sense, strictly speaking, in the elements of 2B, zinc, cadmium, mercury, 3D10, 4S2, 4D10, 5S2, 5D10, 6S2. The metallic bond is weakest in mercury because zinc is a small atom, 2 electrons are participating in metallic bond. Mercury is a big atom, but still 2 electrons only are participating. So, metallic bond is weak because metallic bond strength depends on the distance. inversely proportional to distance. Bigger the size, bigger the gap, weaker is the attractive force. You know, when two species are together, they have strong attractive force. You know, Coulombic attraction F is directly proportional to Q1 Q2 by d square. So, it is directly proportional to charge, inversely proportional to size. Metallic bond strength also depends on internuclear distance. That is why this particular group itself have low melting points, and mercury still, so it is a liquid at room temperature. So, by the same yardstick, now that is the analogy between S and D block. I brought about the chief differences between S and D block. They have low melting points, high melting points, fixed oxidation states, variable oxidation states. If I ask you what is the oxidation state of manganese in its compounds, no one can answer. It can be +2, it can be +4. What is the oxidation state of manganese in its compounds? Manganese in its compounds. It is an impossible question. Oxidation state of manganese in its compounds, it can be +2, in MnCl2 it is +2, in MnO2 it is +4, and in KMnO4 it is +7. So, how can anybody answer what is the oxidation of manganese in its compounds? It depends on which compound. But if somebody asks what is the oxidation state of potassium in its compounds, potassium in its compounds is always +1. We can guarantee the oxidation states of 1 and 2, but there is no guarantee for transition metals. So, they have variable oxidation states. And now, between lithium, sodium, potassium, rubidium, cesium, among these elements, from lithium to cesium, which one will have highest melting point? Lithium, top to bottom, what do you know? Top to bottom sizes increase. Lithium, cesium is the biggest, top to bottom sizes increase. So, only one electron participate in metallic bond. What do you know about alkali metals? 1A elements, they are called alkali metals. So, cesium is very big, but its contribution is only 1. Cesium has many lakhs of rupees, but it gives only 1, because valence electrons are only 1. All of them have NS1 is a general electron configuration, 2S1 in the case of lithium, 6S1 in the case of cesium, 2, 3, 4, 5, 6. So, cesium is almost a liquid at room temperature. The melting point of lithium is around 150 degrees centigrade, and that of cesium borders on the room temperature 27, 28, I do not remember the exact value. So, lithium, the melting point is very high, very less. Why? Number of electrons participating in metallic bond is 1, size is big. So, it depends on two factors. One is a constant, but the other one is a variable, it increases. So, top to bottom in a group of metals, the melting points decrease. There could be 1 or 2 variations, do not mind that. So, look at the S block 1A, they are called alkali metals. 2A, alkaline earth metals. You can learn a great deal just by looking at the names. Alkali means basic. Yes, of course, they are basic. Alkaline earth metals means alkali metals are lithium, sodium to cesium, beryllium, magnesium to barium, right? Both are basic, both are alkaline. Sodium oxide, sodium hydroxide are one and the same, because an oxide when dissolved in a metal oxide when dissolved in water gives hydroxide only. So, magnesium oxide, magnesium hydroxide. So, they both are bases. And what does the name suggest? Alkaline earth metals. Means compounds of these elements are found most on Earth's crust. Earth's crust means whatever the sandy stones, sand, part of water, lithosphere. The lithosphere where you find sand, stones, mountains, etc. So, The compounds of alkaline earth metals are found most on Earth's crust. And the compounds of alkali metals, where are they found? And what does the name suggest? Look here. They are found on earth crust. These are not found on earth crust. So, where are they found? Where will you get compounds of alkali metals? Sodium chloride, potassium chloride. You find them in water bodies. Water bodies, wherever water is there, you can find these compounds. Compounds of alkali metals, compounds of alkali metals, NaCl, NaI, etc. You find them in water bodies, whereas you find them in Earth's crust, other than water. Why? The name suggests that these are water soluble and they are less soluble. Their compounds are not soluble in water. You keep a bag of sodium chloride on your terrace and a bag of calcium carbonate on your own terrace. What will you find after the monsoon? Or what will you find after the rainy season? You will find only calcium carbonate. What happens to NaCl? It dissolves in rainwater, goes down the drain to the sea or whatever water body nearby. Calcium carbonate, limestone, the stone remains there even after the monsoon. Why? Even rain cannot affect calcium carbonate. That is not water soluble. Right. So, first property of alkaline earth metals, they are soft, they have low melting points, and S block elements, alkali metals are soluble, they exhibit fixed oxidation states. So far, so good. And now, when you put these elements to flame, alkali metals give their characteristic color. What do you mean by characteristic color? Each one has its own color. Lithium gives some color, sodium gives golden yellow, lithium in fact gives crimson red. So, all of them give color to flame. Beryllium and magnesium do not give any color to flame. Flame test. Beryllium, magnesium, no color. Calcium, strontium, barium, once again they give color. So, what is responsible for color? Why are some substances colored? Why are some substances not colored? Listen. And that too when put to flame. Alkali metals have NS1, they have an unpaired electron. So, any substance containing loosely held electrons which excite easily, easily means by taking visible light. Difficulty means by taking UV light. Electron gets excited either by UV light or by visible light. No other energy excites electrons. Perhaps you haven't understood my word. No other energy excites electrons. Suppose you give heat to an electron, it doesn't excite, it gets ionized, goes completely out. Excitation means going and coming back. Excitation means going from third level to fourth level and coming back. Excitation. Ionization means going completely out, never coming back. So, all other energies like heat, electricity, they remove the electron completely. They throw the electron outside the atom, which is called ionization. Only light can excite. Light will take the electrons to a higher level, bring it back. Light can be UV light or visible light. So, loosely held electrons excited easily means visible light, which excite excite difficulty, it is UV light. So, only when visible light is taken, a substance is colored. Color is due to visible light, absorption of visible light, absorption of visible light for the excitation of electrons. Excitation of electrons, right? So, alkali metals, they have single unpaired electron 2s1, 3s1, 4s1, which can be excited easily. When you put that to flame, what is the significance of flame? The first the metal melts, atomizes, and then the atom receives the light energy and electrons excite easily. That is why you get the color. So, what about beryllium, magnesium? They have paired electrons close to the nucleus. Pair, 2, 2. Paired electrons close to the nucleus. So, what? They are close to the nucleus means they are held strongly by the nucleus. Nucleus holds the electron strongly. So, what? They do not get excited easily. They do not get excited. I never said they do not get excited. They do not get excited easily. They do get excited by taking UV light. So, a substance, if it takes UV light, it is not colored. I repeat, a substance is colored if only the electrons are excited by visible light. And when are electrons excited by visible light? When the electrons are loosely held. So, I am writing the statement, it is a very important statement. A substance is colored. A substance is colored if only the electrons are excited by visible light. All electrons in all substances can be excited. All electrons in all substances can be excited, but the thing is whether they are excited by visible light or whether they are excited by UV light, that is the question. So, if only the electrons are excited by visible light, the substance is colored, means loosely held electrons only, loosely held. So, alkali metals have NS1, loosely held. Beryllium, magnesium have 2s2, 3s2, strongly held. Beryllium, magnesium, they are excited by UV only. They take UV and they give all visible colors, violet, indigo, blue, green, yellow, orange, red, all visible colors they give out. So, it is white. The light comes out of these substances is white light, magnesium dazzling white. But what about calcium, strontium, barium? Calcium, strontium, barium, they have no doubt 4s2, 5s2, 6s2, but they are paired electrons away from the nucleus. Away from the nucleus. Therefore, they can be excited easily. I never said these electrons cannot be excited. These electrons also can be excited by UV, but only when they are excited by visible light, substance is colored. So, you get characteristic colors in flame. And one very most important property of metals, what is a metal after all? Electropositive, which have a tendency to lose electrons. Tendency to lose electrons is metallic character. And when a substance loses electrons, it is said to be a reducing agent. Reducing agent. So, alkali metals are very, very good reducing agents. And among them, lithium is the best reducing agent. Lithium is the best reducing agent. Why? It has got the least SRP value, least standard reduction potential. Among all metals, lithium Li plus Li, the value is minus 3.05 volts, the SRP. So, what is this SRP and all? We can discuss later in another topic perhaps, but why is lithium the best reducing agent? It is because of their hydration energy. The chief property of any metal is its hydration energy. Metal hydration. What is hydration energy? When lithium ion is in water, it is surrounded by water molecules the negative charge on oxygen minus delta will interact with this positive charge. So, during this interaction energy is released. Positive charge, negative charge interaction, what happens? Q1, Q2 by d square once again. That is called hydration energy. Sometimes a dative bond may also be formed. In the case of lithium, you can even predict a dative bond, means oxygen donating a lone pair is also possible. But hydration, there is no guarantee that it is hydrogen bond formation. Some cases there can be, in some cases there can be dative bond. Most of the time, so in the case of lithium there is a dative bond. Most of the time hydration means metal in positive state interacting with the negative charge of water, partial negative charge. So, this is called ion dipole interaction. This is an ion and that is a dipole. Water is a dipole which has both positive and negative charges. So, even chloride, anions also get hydrated. What is hydration? Interaction between ions, minus and plus delta, plus and minus delta. So, both anions and cations get hydrated and small ions are more hydrated. Small ions are more hydrated. So, lithium ion is surrounded by a large number of water molecules. Lithium attracts more sympathy from water. What will water do? It will try to neutralize the positive charge by giving the partial negative. So, then partial negative O minus delta, small ions attract more sympathy from negative charges of water. Right. Cesium being a large ion, it is a very huge ion, it is less hydrated. So, small ions are more hydrated, therefore, their mobility decreases. They can't run in water. Water molecules do not permit lithium to run, whereas cesium can easily run. So, small ions are more hydrated, less conductive, their conductivity decreases. So, the conductivity of lithium chloride, sodium chloride, etc., lithium chloride is less conductive because small ions are more hydrated. What do you mean by hydration? Water molecules surrounding ions. So, since lithium has very high hydration energy, when lithium solid is converted to hydrated lithium ion, the whole process, there are several steps. Of course, the lithium solid is converted to lithium in gaseous state, sublimation. Lithium gas is converted to Li plus in gaseous state, which is called ionization, and Li plus in gaseous state. I repeat, Li plus in gaseous state, when it comes to water, it is surrounded. This is called hydration. Of course, some energy is spent here, but a lot of energy is released here. So, overall process, when lithium converts to lithium plus, during the overall process a lot of energy is released. So, del H of this reaction is very high. So, because of hydration, if 100 is spent here, 100 is spent here, 500 is released here, net profit is equal to 300. So, lithium loses electrons more easily than any other metal of alkali metals. So, why is lithium the best reducing agent in alkali metals? It is the smallest. So, what if it is smallest? It gets hydrated more. Hydration energy is more. Therefore, small ions are more hydrated. And now, basicity of oxides, we have already discussed that. If you remember basicity of oxides, plus, minus, minus, plus. What is this plus, minus, minus, plus business? Plus means electropositive, metallic, and oxides are basic. So, left to right basicity of oxides, decrease, top to bottom increase. Therefore, lithium oxide, sodium oxide, cesium oxide, top to bottom electropositivity increases. Cesium is most electropositive. So, basicity of oxides increase. So, this is most basic. And between Na2O and MgO, left to right, basicity decreases. So, 1A group hydroxides of 1A hydroxides are very strong bases. In fact, strong bases include only barium hydroxide from the second group, all others are weak bases. So, what are 1A? What are strong bases? Lithium hydroxide to cesium hydroxide of first group, barium hydroxide of second group. Only these 6 are strong bases, all others are weak bases. So, basicity of oxides is over. And now, extraction of alkali metals we discussed in metallurgy, but alkali metals and other highly active metals, they can be extracted by electrolysis of their compounds in molten state only. Only yesterday we discussed this in metallurgy, only in the last class. Alkali metals, other highly active metals, they can be extracted by electrolysis of their compounds in molten state. So, molten NaCl only on electrolysis gives sodium. Aqueous NaCl solution, you don't get sodium, instead you get hydrogen, right. So, Downs process, electrolysis of molten NaCl. Kastner's process, electrolysis of fused NaOH. What do you mean by fused NaOH? Fused also means molten. So, NaOH in molten state, you electrolyze, you get sodium. This is called Kastner's process. Downs process involves molten NaCl. So, sodium is extracted in Downs process and Kastner's process. And when you take aqueous NaCl solution, brine, this is called aqueous NaCl solution. This is called 10% aqueous NaCl solution is called brine. You have Na plus here, Cl minus, H plus, OH minus. And to cathode, the negative electrode, hydrogen goes, H plus goes and becomes H2. To anode, Cl minus goes, positive electrode, Cl minus goes and becomes Cl2. So, what is remaining? NaOH. So, this is called Nelson's cell. Nelson's cell, listen. What are the products? You get hydrogen at cathode, chlorine at anode. Both chloride and hydrogen are gone. Sodium hydroxide is remaining. Therefore, manufacture of NaOH means Nelson's cell. The remaining solution is NaOH. Chlorine can also be obtained. So, when you study manufacture of chlorine by Nelson's cell, you get chlorine here, NaOH here. That is about their extraction. And then, let us look at questions. First question. Which one of the following reactions represents the oxidizing property of H2O2? Look here. Forget the coefficients 2 KMnO4, 3 H2SO4, forget all those things. Just look at KMnO4 on the left side, H2O2. And what is happening to manganese? It becomes MnSO4. So, what is happening? Manganese plus 7 to plus 2. So, manganese is decreased from plus 7 to plus 2. Decreased, reduced. So, H2O2 is reducing manganese. It is not an oxidizing property. In oxidation, you have to develop others. Here you are destroying others, plus 7 to plus 2. So, H2O2 is reducing manganese from plus 7 to plus 2. So, this is a reducing property. Look at the second choice. 3 FeCN6, K3 means iron 3. Reactants, you just look at K3 FeCN6, you should be able to immediately notice the oxidation states. You can practice that in no time. This is minus 6, this is plus 3, iron plus 3. The quicker you notice, here the emphasis is on iron only, because potassium, the oxidation state will never change. Potassium K plus to K0, no one can bring that change. So, the reactants you have this. H2O2 is responsible for this. And what is the product? K4 FeCN6. K4 FeCN6. So, you should immediately notice that plus 3 to plus 2, plus 4 minus 6 plus 2. You observe the change in oxidation number. So, what is H2O2 doing here? H2O2 plus 3 to plus 2. This is once again called reduction. So, H2O2 is acting as a reducing agent. And then PbO2 to PbO. You just observe the chief PbO to PbO. What is happening? Plus 4 to plus 2. Once again H2O2 is decreasing, reducing the oxidation state of lead. So, H2O2 acting as a reducing agent. So, in the first example reducing agent, second example reducing agent, third example reducing agent, and you observe when H2O2 acts as a reducing agent, the one of the products is always oxygen. When H2O2 acts as an oxidizing agent, one of the products is always oxygen. Remember that. Means H2O2 gives an oxygen, the other fellow gives an oxygen, it becomes O2. H2O2 gives an oxygen, you can easily observe this here. PbO2, H2O2, H2O2 gives an oxygen, PbO2 gives an oxygen, both the oxygens become O2, PbO plus H2O. So, how do you get oxygen in reactions of H2O2? H2O2 gives an oxygen, the other fellow also gives an oxygen. This oxygen and this oxygen assembled O2. So, H2O2 is giving an oxygen means oxidizing agent. H2O2 is giving an oxygen, oxidizing agent. So, and look at the last one, Ki to I2, Ki to I2. Who is doing this? H2O2. I minus to I0, the oxidation state of iodine is minus 1. So, minus 1 to 0, minus 1 to 0 means H2O2 is increasing, oxidizing. And you can see there is no O2 on the right side. So, first question, the answer is 4. Second question, which of the following statements are correct for alkali metal compounds? Superoxides are paramagnetic in nature. What is a superoxide? We discussed it long ago, KO2, potassium superoxide. So, O2 minus means 8 plus 8 plus 1, 17. Odd number, odd means para. You remember that? Total number of electrons, odd number, it is paramagnetic. Even number, it is diamagnetic. I told you O2, B2, N2, 2 minus are exceptions. If you forget these three, O2, B2, N2, 2 minus, if you forget them, total number of electrons, odd number, then it is para. So, potassium superoxide means KO2. You should know that O2 minus is superoxide. This we almost discussed in the first class. O2 minus is superoxide. O2 2 minus is peroxide. O2 minus, 2 oxygens, 1 electron, 2 oxygens, 2 electron, 1 oxygen, 2 electrons, 2 oxygens, just 1 electron, minus 1 by 2. So, this is oxide, normal oxide. This is a normal oxide. Now, so superoxides are paramagnetic in nature. The basic strengths of hydroxides increases down the group. LiOH, hydroxides, CSOH. Top to bottom, what happens? Electropositivity increases. So, electropositivity, oxides are more basic, oxides and hydroxides are more basic. Top to bottom, what is that? Basic strength of hydroxides increase, that is correct. So, A is correct, B is correct. What about C? the conductivity of chlorides in their aqueous solutions decreases down the group. You see, conductivity of chlorides, he is talking about LiCl, NaCl, KCl to CSCl. Conductivity. Small ions are more hydrated. Small ions are more hydrated, less mobile, less conductive. Large ions are less hydrated, very few water molecules. So, conductivity, what happens? The conductivity of chlorides increase. Therefore, C is wrong. The basic nature of carbonates in aqueous solution is due to cationic hydrolysis. Basic nature of carbonates, look here. Let me talk about sodium carbonate. Sodium carbonate is basic, right? Na plus is the cation. CO3 2 minus is anion. Suppose Na plus reacts with OH minus. Suppose Na plus reacts with OH minus. What happens? You have H plus and OH minus in water. There are two possibilities. CO3 2 minus may or may not react with H plus. Na plus may or may not react with OH minus. Water. Suppose CO3 2 minus reacts with H plus. Means CO3 2 minus has eaten H plus, taken away H plus. Now OH minus remains, solution is basic. So when will a solution be basic? When the anion eats H plus, eating. When the anion eats H plus, OH minus remains and the solution will be basic. So the basic nature is not due to cationic hydrolysis. Na plus does not react with OH minus. Na plus does not eat OH minus. I will give you a generalization. The cations of strong bases LiOH2 CSOH and BaOH twice, and anions of strong acids, so what are the cations? Li plus, Cs plus, barium 2 plus. The cations of strong bases Li plus, Cs plus, Ba2 plus, anions of strong acids perchlorate, sulfate, I minus, Cl minus, Br minus and NO3 minus, I minus, Br minus, Cl minus. So these are the cations of strong bases, these are the anions of strong acids. These 12, they don't undergo hydrolysis. Remember this generalization. Cations of strong bases and anions of strong acids. So this fellow does not undergo hydrolysis. Undergoing hydrolysis means eating H plus or OH minus. This fellow doesn't eat OH minus. This fellow eats H plus. So H plus is no longer there. OH minus, basic. So a solution will be basic if only the anion undergoes hydrolysis. A solution will be acidic if only the cation undergoes hydrolysis. Aqueous NH4 Cl solution. You have H plus and OH minus. You know about Cl minus. He doesn't eat H plus. No. Cl minus is an anion of A. Cl minus is an anion of A. Strong acid. So, but NH4 plus, he eats OH minus. So, OH minus is not there in water. H plus is there, acidic. Right. Therefore, which are right? Superoxides are paramagnetic, basic strength increases, A and B. So, answer is 2. An oxide of an element is a gas and dissolves in water to give an acidic solution. Look here. Oxides of 1 and 2 groups, Li2O, MgO, MgO, they both basic oxides. Metal oxides are basic. So, second group, 0 group, they don't even form oxides. Second group, 0 group, no. Eighth group means iron, cobalt, nickel, once again. So, second group, he is talking about second group, magnesium oxide, metal oxide, basic. Eighth group, iron, cobalt, nickel, once again, metal oxides, basic. 0 group, they don't form any oxides. So, which can only be acidic? Fourth group. Fourth group means carbon dioxide acidic, silicon dioxide acidic. Of course, germanium, others we don't know, but carbon dioxide. Fourth group oxides are acidic. Second group oxides are basic. Fourth group oxides for carbon, silicon are acidic, and eighth group metal oxides basic, and zero group they don't form any oxide, helium, neon, what oxides they form. Next question. What are the metal ions present in cornellite? Cornellite is KCl, MgCl2, 6H2O. This is an important ore of magnesium. So, you have potassium, magnesium. So, which is the answer? 1. Fifth question. Which one of the following reactions does not form a gaseous product? We already discussed that. PbO2, H2O2. PbO2, H2O2. H2O2 loses oxygen, PbO2 loses oxygen. You know why? H2O2 has weak peroxy bond, breaks easily. PbO2 wants to become PbO because of inert pair effect, +4, +2. So, PbO2 wants to become PbO, which is called inert pair effect. So, he loses an oxygen, he loses an oxygen, you get O2, a gaseous product. So, first option you get O2. Second option, acidified KMnO4 H2O2. KMnO4 H2O2. Here, manganese, potassium, permanganate is an oxidizing agent, he gives oxygens, he also gives oxygens, therefore O2 is there. PbS plus H2O2, it is a very interesting question. PbS plus H2O2, what happens is H2O2 gives oxygen atoms, but only one, mind you. H2O2 wants to become H2O, that's all. H2O2 wants to become H2O. So, it gives only one oxygen. It gives only one oxygen. So, PbS, non-metals want to go to maximum oxidation state, PbSO4. So, I want 4 oxygens here. How can I get 4 oxygens? I should take 4 H2O2. When I take 4 H2O2, I get 4 H2O. This is a solid, this is a black solid, and this is a white solid, and 4 H2O2, 4 H2O is a liquid. So, you don't get a gaseous product in the third option. Wait a minute. PbS, you must have studied about this. Oil paintings contain lead. Oil paintings contain oil paints. Paints contain lead. And over a period of time, say 100 years, 500 years, oil paintings, they absorb atmospheric sulfur dioxide and they become lead sulfide. They become black. So, old oil paintings are black. You can't see any faces because a black shade is appearing. So, H2O2 is sprayed on old oil paintings wherein you get lead sulfate white. So, in museums you must have seen some white patches on the old oil paintings. The whiteness is because of lead sulfate. So, one of the important uses of H2O2 is it restores the color of old oil paintings. It restores the color of old oil paintings. But very funnily, the oil painting is black, you can't see anything. Now, even after H2O2 it is white, then also you can't see anything. Black coating, next is a white coating. What face you can see here? So, H2O2 restores the color of old oil paintings. What about the last one? Cl2 plus H2O2 is very easy. Cl2 plus H2O2, you get 2HCl. 2HCl plus O2 is an oxidizing agent, it is a reducing agent. Right. Now, so fourth case also you get a gaseous product. Third option you don't get a gaseous product. Sixth question. The molecular formula of potash alum is, it is K2SO4, Al2SO4 thrice, 24H2O. K2SO4, Al2SO4 thrice, 24H2O. Why is it called potash alum? There can be several alums. Alums are +1 and +3 sulfates. Means potassium +1, aluminum +3. So, a sulfate in +1 oxidation state and a sulfate in +3 oxidation state. So, this one is potassium alum. you can have chrome alum where Cr2SO4 thrice is there, you can have ammonium alum where NH4 plus is there, ferric alum Fe3 plus. So, there are different varieties of alums. Next question. Which one of the following is used an acidic flux in metallurgy? Acidic flux means as acidic flux. As you know well, last one or two questions I take up as revision questions. So, it should be acidic. What about calcium oxide? Metal oxide, basic. SiO2 is acidic flux. You may get a doubt, SO2 is also acidic. I agree. But if you treat CaO plus SO2, you get CaSO3, but that may not be formed as slag. Not only that, how can you mix a gas into this one? SO2 is a gas. Silicon dioxide means sand. Silicon dioxide means sand. You can bring any amount of sand and put. Therefore, SiO2 is used as acidic flux. SO2 may be used, but that is not used in practice. That is it. Because it is difficult to bring in a gas and mix that to a molten mixture. So, SiO2 is the answer. A mixture of sodium oxide, calcium oxide, sodium oxide, calcium oxide, right? Dissolved in water and saturated with excess of carbon dioxide. You dissolve that in water. You get NaOH and CaOH twice, calcium hydroxide, which is called lime water. And now, what are they doing? Excess carbon dioxide. When you add carbon dioxide, what happens? You get CaCO3, milky white precipitate. Milky white precipitate. So, lime water turned milky by carbon dioxide, all of us know this. Lime water turned milky by carbon dioxide. But when you send excess carbon dioxide, what happens? It will be calcium bicarbonate. It will be dissolved once again. The milky whiteness goes dissolved. And what happens to sodium hydroxide? It becomes sodium carbonate. Okay. What happens to the solution? Solution, you will have sodium carbonate, calcium carbonate. But they are not referring to this, means they are using the word excess only to tell you both sodium hydroxide and calcium hydroxide are there. So, the solution contains sodium carbonate, hydroxide plus carbon dioxide, CO2, it should be HCO3 and becomes Na2CO3 in water. So, sodium carbonate and calcium carbonate. If you take excess here, you get calcium bicarbonate. No option contains calcium bicarbonate. Why did they use the word excess? They use the word excess because you have two hydroxides here. Okay. So, you have to answer this question logically. But lime water excess carbon dioxide means it must be calcium bicarbonate. Lime water excess carbon dioxide. But now 9. What is the reaction occurring at anode in Downs process? I did mention Downs process. Downs process means molten NaCl. Na plus Cl minus. Who will go to anode? Anode means positive, Cl minus. Therefore, anodic reaction is 2Cl minus Cl2 plus 2 electrons. Where do you find that? Third option. Last question. Which process used for the removal of hardness of water? Hardness of water, it can be removed by called Calgon. Calgon means sodium hexametaphosphate. Sodium hexametaphosphate. Na6PO3 6 times. Na6PO3 6 times. Sodium hexametaphosphate. So, that Calgon adsorbs the calcium and magnesium ions and removes hardness. That is first option. Okay. We take leave for today.